Okay, so we're now going to see how noisy channel methods are used as the basis for modern machine translation. So we looked at noisy channels before. The idea was that we have a source signal that gets transferred through a channel, and that's our model of communication. And the noisy channel model is essentially a parametric probabilistic model of language and translation. So let's see how it works. We're given some foreign language sentence, F, and we have to guess the English translation, E. So we're going to think of this process as follows. We have the English sentence E, the one that we're trying to guess, and we convert it to a foreign language sentence using an encoder from E to F. So now we actually observe this F and we want to guess back the original E. So this is done through a decoder that gets the F as input and produces E as the output. Actually, it doesn't produce E, it produces E prime, but we want to pick such an E prime that is as close as possible as to the original E that was really the English sentence. So now we have a translation model and a language model, and we're going to pick the E that maximizes this probability. So we want the probability of E given F to be largest, and we're going to model this using the Bayesian theorem by representing it as the product of the translation model, F given E, and the language model, E. So P of E just means, given this English string, what's the probability that it forms a valid English sentence? And P of F given E says, if we have this particular English string E and this particular foreign sentence F, what's the probability that F was produced by E? So let's look at an example. Suppose that we want to translate from French this expression, une fleur rouge. Let's look at several different candidates. Again, we have an infinite number of candidates for English. We're just going to look at some of them and see how this method works. So the first one is a flower red. The second one is red flower a. Third one is flower red a, and so on. So let's see what are the values for P of E and P of F given E and the product of those for each of those examples. So our flower red has very low P of E because a flower red is not a trigram that you expect to see in English. However, it has a high value for P of F given E because it has the exact words that we expect to see in that translation. And then if we multiply those two, we're probably going to get a relatively low score. The same thing applies to the next two lines of this table. A red flower A is also very good in terms of its relationship to the foreign sentence, but it's not a legitimate English translation. And same thing applies to the third one. Now let's look at a red dog. Now a red dog is going to have a much higher P of E because it's something that you expect to see in English. But P of F given E is going to be low because the words here are not the ones that we saw in the French sentence. Next one is dog, cat, mouse. That is going to have low values for both of those features. And finally, a red flower is going to have high values for both, and therefore a high product. So the idea here is if we can estimate P of E and P of F given E and multiply them together, we can rank all the candidate English phrases based on this product and pick the one with the highest score as the correct translation. So here's an example. We want to go, for example, between English and Chinese. We have some text in Chinese. We want to find for every English sentence the probability of the Chinese sentence given the English sentence, multiply it with the probability of the English sentence, and that is going to give us an estimate of the probability of the English given the Chinese. Okay, so noisy channel models are used not only for machine translation, but for many other tasks. For example, for text-to-text generation or summarization, where the input is a long document and the output is a short document. So in the lecture on summarization, we talk about this method. But also things like text-to-signal, speech recognition, OCR, spelling correction. In each of those cases, we have as input one type of text or representation, and the output is another type of text or representation, and the noisy channel converts one to the other. So specifically in OCR, we have the probability of the text given the pixel map is the product of the probability of the text times the probability of the pixels given the text. So the IBM model that was developed in the early 90s and is probably one of the most fundamental contributions to natural language processing goes like this. We're going to start with a sentence in one language, and then we're going to perform a sequence of transformations to it until we get to the sentence in the target language. So some of those transformations may look very unintuitive. However, they have been picked for very good reason. They are all relatively possible or straightforward to implement computationally. So this is an engineering achievement more than a linguistic achievement, because we want a system that works, even if it's not necessarily based on the way that humans actually do the translation. So bear with me for a second and you'll see what the story is, and we can discuss later if it makes sense. So here's how we want to translate from English to French. I watched an interesting play. So in the first step, which actually the order of steps here in this example doesn't match the order that the IBM system uses, but it will still give you a good idea how it works. So in the first step, we're going to reproduce each of those words in English as many times as we need to get the actual number of words in the French translation. As we saw before, the word play in English is translated as 3 words in French. So we're going to have something like this. I watched an interesting play. So the reason why we have 3 plays is because the French translation of play has 3 words. And the reason why we have 2 words for watched is because the French translation of watched is also going to have 2 words. Okay, the next thing that we need to do is to now figure out the right word order. So because in French the nouns and the adjectives appear in a different order than in English, we're going to switch their order. We're going to get I watched, and play, interesting. And then in the final step, we're going to convert each of those English words into one of the French words that corresponds to it. So I becomes J apostrophe for je, watched becomes a vu, play becomes pièce de théâtre, and interesting becomes intéressant. So this is how the IBM model works, roughly. We have essentially 3 sets of probabilities. The first one is the so-called fertility probability, which tells us what's the probability that a word of length, an expression of length I in one of the languages is going to be translated as an expression of length j in the other language. The second is the word ordering or distortion. So it tells us what's the probability that the word in position 7 in one language is going to switch to position 8 in the other language, and vice versa. And finally, we have the translation probabilities, which tell us what's the probability that a certain word in English gets translated to a certain word in French. And each of those probabilities is automatically obtained by using a method called EM, or expectation maximization, from pairs of aligned sentences in those 2 languages. So I'm not going to go through a lot of detail about those models. I just want to list them here. There are 5 EM trained models. So translation, alignment, and fertility, the ones that I already mentioned, and also models 4 and 5, which include something called class-based alignment and non-deficient algorithm. Here are some of the steps that we need to undertake in order to do machine translation. We first have to tokenize the input document into words. Then we have to perform sentence alignment. So most of the time we're going to have 1-to-1 alignments, especially when in the case of good parallel corpora such as the Hansards, or perhaps 2-to-2, which are relatively rare. That's when sentence A and B into one language get translated into, let's say, sentences X and Y in the other language, but A doesn't exactly match to X and B doesn't exactly match to Y. And finally, we have other examples, for example, 2-to-1 or 1-to-2 mappings, where one sentence in one language gets split into 2 or more sentences. So the method that has been used first on this problem was by Church and Gale, and it was based on sentence length. So they look at sequences of forograms and cognates between the languages. This especially works for languages like French and English. And this is the kind of alignments that they get. So they look at the paragraph length in English and the paragraph length in German. And you can see that the paragraph lengths are highly correlated. The scatter plot diagram shows you that very easily. And then in their output, they see that most of the pairs of sentences have a 1-to-1 mapping. 89% of them have that. And there are a few examples of 2-to-1 and 1-to-2 alignments, or 1-to-0, 0-to-1, those are extremely rare, less than 1%. And finally, a few examples, a little bit over 1% of 2-to-2 alignments. So once you have performed sentence alignment, you can apply the IBM models 1, 2, 3, and so on if necessary to learn the actual translations, fertilities, and distortion probabilities. So let's look briefly at IBM Model 1. So IBM Model 1 is based on alignments of sentences. So for example, you have a pair La Maison Bleue in French with the blue house. And you look at all the possible alignments. There can be things like 1, 2, 3, which means that the first French word becomes the first English word, the second becomes the second, and the third one becomes the third one. The second alignment is 1, 3, 2, which means that the first French word becomes the first English word, but then you swap the order of the second and the third one. And there are other combinations. For example, you can say that the second English word doesn't exist in French, but the third English word corresponds to the second and third French words. Or you can go even to an extreme and say that all three words in French get translated as the first word in the English sentence, but the second and third English words did not appear in the French at all. So there's a certain number of such alignments, and you have to consider all of them. And at the beginning, you're going to assume that all of them are equally likely, and then the EM algorithm is going to tell you which one is most likely, and at the same time give you the most likely alignments between individual words. So we're not going to go into a lot of detail about IBM models 1, 2, and 3. However, if you're interested in that, you can go and read an excellent tutorial by Kevin Knight, which is available on his website. And you can also download an implementation of a statistical machine translation system called Moses from statmt.org. We're going to continue in the next segment with some advanced methods for machine translation.